And, and then I would love to just take a moment and introduce Kate. Kate Keahey is one of the pioneers of infrastructure cloud computing. She created the Nimbus project, which is recognized as the first open source IaaS. Kate continues to work on research aligning cloud computing concepts with the need of scientific data centers and applications. Today, Kate leads a Chameleon project, which provides a reconfigurable, large-scale, and open experimental platform for computer science research. To foster the recognition of contributions to science made by software projects, Kate has also co-founded and serves as co-editor-in-chief of the SoftwareX Journal, a journal with a new format designed to recognize software contributions. Kate is a scientist at Argonne National Labs and a senior fellow at the Computation Institute at the University of Chicago. Today, she is here to talk to us about experimenting from edge to cloud. Kate, it's all yours.
Thank you so much. Thank you very much for inviting me, and thank you for the lovely introduction. And to extend this introduction, of course, I work on many scientific instruments in software and scientific instruments in infrastructure. And those could be scientific instruments that support domain sciences or computer science. And today I'm going to talk about the specific infrastructure project called Chameleon, so a very small, very adaptable reptile, and how it supports computer science research, right? So first of all, scientific instruments. I think that most of us have some sort of concept of a scientific instrument. So biologists might use microscopes, astronomers might use telescopes, physicists have a whole range of very interesting instruments, many of them very, very large. ITER and the Large Hadron Collider at CERN, famously so large that no single country could afford them. But what does it mean to develop an instrument for computer science research, right? Now, computer scientists, system scientists in particular, work on things like creating, designing new operating systems, maybe new virtualization solutions, networking protocols, storage protocols, new algorithms, and so on and so forth. And to design those things, what you need is access to as large as possible and diverse amount of hardware, usually powerful hardware, where you can test your ideas, right? And you can formulate your hypothesis and then evaluate it. And in order to do that, for system science in particular, that hardware needs to be reconfigurable at a bare metal level, right? So very deeply reconfigurable, generally speaking, very non-prescriptive configuration on which you can build whatever you need to build. So there's one thing that is common across all scientific instruments, and that's the fact that they need to evolve, right? So the telescopes of a few centuries ago are not the telescope arrays of today, and the microscopes of a few centuries ago is not what we use today. So I'm going to talk today about the evolution, about Chameleon, of course, as a scientific instrument, but also about its evolution to allow people to address new scientific questions, right? So there's a reason why we have telescope arrays these days, rather than just a simple telescope, right? The frontier of science has moved, and it has moved in computer science as well. And in particular, the place that it's moving today is exploration of all sorts of issues that are supported by the emergence of the Internet of Things, right? So Internet of Things devices, I'm sure everybody here has heard of Internet of Things, very often very inexpensive devices that can be deployed at scale and can be used to instrument our cities and our fields and forests and rivers and so on, and create a large instrument that could rival the Large Hadron Colliders and the ITER projects and things like that that we work with today, right? And while those large instruments are hardwired in order to perform their function, the instrument that will allow us, that uses the IoT devices, will not be hardwired. It will be connected by a very adaptable fabric called software, right? It's software that you can use and reuse to answer various different scientific questions. And those will be questions that were out of reach before, right? Because again, we can deploy those devices at scale and build an instrument that will allow us to change the planet into one global instrument and answer science questions that were out of reach before. But before that happens, we have to advance computer science, advance system science to answer a host of questions in scale. Like there will be a lot of those inexpensive devices, data producing devices. How do we deal with that? Security, all sorts of questions in dynamicity, right? Devices that come and go, that move in and out of reach, that are otherwise affected, resilience, data information workflows, and so forth, right? And many others. And in order to explore those questions, we need the freedom to experiment. And to experiment, as computer scientists, as system scientists, we need a scientific instrument that will support that experimentation. So I'm going to tell you a little bit about what Chameleon is today and how we just started evolving to address this new science frontier. So Chameleon in a nutshell, of course, chameleons are known for their adaptability, right? So it's a test bed that adapts itself to your experimental needs. It's deeply reconfigurable at bare metal, right? So you can have, you can allocate a bunch of nodes and you will be the only person working on those nodes. And of course, you will have root on those nodes and you will be able to reboot them and boot them from custom kernel. If you're developing a new operating system, have access to serial console and so on and so forth. Now, we do also have a small KVM, a small virtualized cloud. Why? Because it's much cheaper to give users virtual machines, right? This allows you to subdivide one node into multiple nodes. And therefore, we can give them to users for a longer time, right? And some experiments in systems, let's say in performance variability or in power management, really do need bare metal. And some, many security experiments, for example, and some of the resource management experiments don't, right? And for those experiments, a virtualized cloud is a much better solution, right? So Chameleon is mostly a bare metal cloud, but also supplements with KVM cloud for projects that can use that. Now, we're trying to give users access to as large scale as possible, but that has to be balanced through diversity. And over the years, we found that our users are, in fact, more interested in diversity and up-to-date hardware than necessarily large scale, right? Large scale can be emulated for many experiments, whereas diversity is much harder. So we originally invested in large-scale homogeneous partition, and in terms of our budget, large scale was 15,000 cores, which of course is nothing in comparison to supercomputing centers. But we do have around 6 petabytes of storage that is available in various configurations. Some of this is global store, some of it in various interesting configurations in different nodes. And originally at 2 sites, at University of Chicago, which is where I'm speaking from, and Texas Advanced Computing Center. And then actually our University of Chicago hardware is in the ALCF Advanced Leadership Facility machine room at Argonne. So both of those sites are large supercomputer centers. And they are connected via a 100G network. So we're also supporting experiments with large flows, right? So large storage, large compute, and large flows over the network. But we also invested in diversity, right? So we've got support for ARMs and Atoms. We've got FPGAs are putting more. We've got various different generations of GPUs, so several GPU clusters, very expensive GPU clusters, and interesting networking hardware that allows you to experiment with software-defined networking at the edge, right? There's another test that is being built now that allows you to experiment with networking in the core. And so what we also did is we packaged Chameleon, we packaged the recipe to deploy those things on different sites, to deploy the Chameleon infrastructure. T stands for Chameleon infrastructure on various different sites. And we now have smaller sites at Northwestern, at NCAR, just configured just in time for the student cluster competition at supercomputing. There's another one being configured at IIT and a few other institutions that are in more initial stages. Now, what makes Chameleon a little bit different from experimental infrastructures that came before it is that we made a very conscious design decision to build the system on top of a mainstream open source infrastructure. Right? That infrastructure is called OpenStack. It's a cloud implementation. Many of you may be familiar with OpenStack as something that deploys and manages virtual machines. For us, it manages bare metal. It has a component called Ironic that manages bare metal. But in order to satisfy our use case, right, in order to give users the experimental capabilities that they needed, we had to extend it to support networking experiments, to support advanced reservations. So in fact, our team contributed the Blazor components to OpenStack. It's a top-level OpenStack component now, and make many other extensions to enable science. But building on mainstream technology gives us many advantages. So number one, there's familiarity for users and operators as well, right? And if they're not familiar, they require transferable skills. You can put on your resume that, yes, I'm familiar with OpenStack, right? Number two, we are relying on contributions of community that numbers in the thousands. And of course, we're contributing to that community as well. And then, of course, very important, last but not least, there are many mainstream tools on the market that convert between OpenStack and, for example, commercial clouds, right? That makes it much easier for our users to now create experiments that span Chameleon and commercial clouds as well. And you may want to do that, right? If you want a higher degree of distribution, or if you're experimenting with commercial clouds specifically, assessing price limits and things like that. And finally, we also invested in reproducibility, repeatability, and sharing. Right? So if you think about experimental test beds, the important thing for them is to support as large a set of experiments as possible. You could also increase their impact by supporting as many users as possible, right? So making easy to use interfaces, for example, so that more and more users can use it, democratize access to the testbed, and so forth. But then there's another dimension, which is you can make those users more productive, but facilitating sharing between them, right? So you don't have to do your research from scratch. You can really reuse something that somebody else produced. And I will touch on all those aspects, most importantly on expanding the reach of the testbed. In other words, multiplying the number of experiments that we support via expansion to edge. But I will also talk at the end about reproducibility and sharing. Okay, so a few numbers for Chameleon. So Chameleon has been operational since 2015. In that amount of time, we managed to serve over 6,000 users, working on 750, over 750, is closer to 770 now, of projects in research, education, and emergent applications, right? Those are the three areas that Chameleon supports. We don't support production science. It's primarily a resource for computer scientists. A few words about Chameleon hardware. So what you see on this diagram is what we started out with. So we had two sites connected by a 100G network. We had 10 racks of Haswell machines at TAC, and two identical racks at University of Chicago. And then at TAC, we also had a storage system, very large storage system, still have it, of course, as well as many different heterogeneous hardware bits in various interesting configurations. In phase 2 of Chameleon, which started in 2017, we added more racks. So we added some racks of Skylake, one at TAC, two at University of Chicago, then also a rack of Cascade Lake at TAC. We are now in phase 3 of Chameleon, and we're about to add another couple of racks of Cascade Lakes at University of Chicago. We'll probably announce that in a week or so. But also, in some ways, more importantly, what we added was connections to other NSF funded testbed. So there's an NSF funded testbed called CloudBank, which provides access to commercial clouds. We are now federated with them. So Chameleon has access via Identity Federation, so does CloudBank. So you can log in with one password to both and run experiments over commercial clouds and Chameleon. And we've got a Jupyter notebook that allows you to, really documents the recipe for doing that. We have Chameleon associate sites. Those are the sites I mentioned earlier at Northwestern, at NCAR, at IIT that are popping up that other people are configuring, joining Chameleon, providing more resources to the project. And very importantly, we're also working with other NSF testbeds that support other types of experimentation. So Fabric supports core reconfigurable network experimentation. There's a range of power projects, and I'm going to talk about one of them later on, supported by NSF to provide experimentation with wireless networks. So we have connections to all those projects. We are federated with them in various ways. All that goes to enable as many experiments as possible that do sophisticated networking with cloud resources and edge resources and wireless networks, all of those things together. So this is the hardware. Now, if you were to come to the testbed, and this is just some detail about what the hardware is, but if you were to come to the testbed, what would you see as a user, right? So as a user, you've got this experimental workflow that starts with formulating a hypothesis. Then you have to figure out what resources you're going to use to test that hypothesis, right? So if you're experimenting with machine learning, you might need a GPU cluster, for example. Then you need to somehow gain temporary ownership of those resources, of those GPUs. So let's say allocate 4 nodes with various GPUs on them for a week, such that they are available to you for exclusive use. Then configure those resources. And then finally, you're running your experiment and monitoring. So for all those 4 stages of the experiment, we provide interesting discovery, resource discovery capabilities. Among others, we version the testbed, and that allows people to reproduce experiments of others in a more controlled way. We support allocations, not just of nodes, but also of networks, of VLANs, and of IP addresses, IPv4 very much in demand. We also do provide on-demand reservations, of course, which are a special case of advanced reservations. But if you come to our GPU clusters, for example, chances are that on-demand nothing will be available, right? So it makes sense to look a little bit ahead, make an advanced reservation, and especially if you have a paper deadline or a demo, that comes in very, very handy. And then once you have those resources, you can reconfigure them at bare metal level. We provide some appliances, we provide some images, and including orchestrated images that represent, for example, cloud configurations or virtual clusters or things like that. So you don't have to start from scratch. You can start from images that we provide, and there are many of them, and they support popular applications like TensorFlow on our CUDA images and so forth. Then you can take a base image like this, you can configure it further to support the needs of your experiments. Once you're done with the configuration, you can save your work, right? You can snapshot the image, boot from that same image. This is to save you that configuration next time around when you come to experiment. And then we also integrated the testbed with Jupyter. And I'll talk about this more later, but this is a very useful interface for many of our users, right? They like from one Jupyter notebook to create their experimental environment, run their experiment, and then process the data from that experiment. And then also we have a host of network reconfiguration mechanisms, in particular network stitching, which allows you to create a wide area circuit, isolated wide area networking circuit, and bring your own controller, which allows you to experiment with software-defined networking. Now, all these capabilities are authenticated via federated identity. That's what allows us to federate with other testbeds, and you can access them via a GUI, via command line interface, and I already explained via Python and Jupyter. And if you want to learn more about this, we published a paper at ATC Usenix ATC last year, where we also discussed various design choices that we made in designing Chameleon. Okay, and so a quick gallery of what our users were doing on the testbed. So this is one of our early users, a student from University of Pittsburgh. She was comparing containerization and virtualization for high performance applications, right? And she needed various capabilities from the testbed. She needed bare metal reconfiguration, the ability to boot from custom kernel, serial console access, snapshotting, and up-to-date hardware. And here's another example from my colleague Swan Peranu at Argonne National Lab. He develops exascale operating systems, and here he is demonstrating his work on Chameleon. His requirements for a testbed very similar to UU. Here's another example of a security project, this time from a group of students at University of Arkansas at Pine Bluff. They were cataloging cybersecurity attacks, and this is a good example of a project that just needed a virtualized cloud to support their research, right? So more efficient use of resources from a project from a very small university that might otherwise not have had access to this type of resources. Networking experiments, here's a group working on the creation of virtual software-defined exchanges. And what they needed to do is the ability to create dynamic VLANs and stitching, right? So again, creating wide area network circuits and managing complex deployment, which we support via orchestration. And nowadays, people like to use Jupyter for that. A couple of our students who won an award for their research at Supercomputing 17, they became semi-finalists in the ACM student research competition. They both worked on data science projects. One of them needed access to state-of-the-art GPUs, and the other one needed storage in various interesting configurations. And here's a very interesting experiment from a student from University of Massachusetts. And she was working on adaptive bitrate video streaming, and you see her experimental configuration up there is quite complex, right? It has no fewer than 4 switches, 2 network circuits, multiple nodes. And she was actually one of our first users of the Jupyter integration. And working with her, we realized the potential of Jupyter for packaging experiments for repeatability. And I'll go back to her experiment later. One of the University of Chicago students working on power management. And then last but not least, this year and really the previous year, we started noticing that more and more of our students want to work on edge and IoT applications. And they do all sorts of interesting research. If you are interested in general to see what our users do on Chameleon, you can go to our blog, and there is a tab for user experiments. Every month, we profile one experiment from our users. We do an interview with them. Those are just experiments that were profiled this year, right? So what users do is they work on biometrics. Here, they were experimenting with systems that recognize the difference between a face and a mask, right? Or between actual fingerprint and a fingerprint spoof, right? This type of data is typically private, and people don't allow moving it from where it is collected very often. And so what researchers came up with is something called federated learning or distributed learning, where you can train a model on a data that is available only locally, and then you have a facility that aggregates those models. So different models learn different things, and then they aggregate that learning to produce a better model from this aggregate. And then network tracking, fingerprinting for IoT devices. So those are 3 projects that we profiled this year, right? 3 very interesting projects, and they were really all working on edge computing. But they were using Chameleon to, in a sense, to emulate edge computing and in order to progress with their research. And of course, to some extent, they can do that. But there are certain questions that you can't answer in emulation or simulation, right? So if you're thinking, for example, about how much power edge devices are going to use running your algorithm, that's very hard to answer, right? You have to have a special kind of emulator to do that. And, there are questions about fidelity and so forth. So what could we do for those users, right? So in phase 3 of Chameleon, sort of started asking the question, how can we extend the testbed to support that type of experimentation? And the answer to that was, well, we need a testbed, an edge testbed, right? A testbed that supports those edge devices as first-class citizens. And talking to our users and also, both via surveys and individually, a lot of our users were saying, well, we would like something that is exactly like Chameleon, but for edge devices, right? We want all the features, in particular, those Jupyter notebooks integrated with the testbed, exactly the way it is. So that was the sort of first thing that we proposed. But then many users were saying, no, this is not right? Because those edge devices, they don't sit in the data center. And the whole point of those edge devices is that they sit somewhere on the edge, right, in the wild. And typically, they are connected to various IoT devices like cameras or various types of actuators or software-defined radios. And furthermore, technically, those devices are not database servers, the data center servers, right? They're not server class, they don't support IPMI or anything like IPMI, right? So you can't do bare metal configuration with them easily or not the same way that you're doing with Chameleon, right? And there are many, many other challenges that they were pointing out. So we sort of decided to walk a balance between those two sets of requirements, propose a test bed, right? Implement the test bed as quickly as we can, and pilot it with as many user groups as we can and see what happens, right? So what we ended up with is reconfiguration via container deployment, right? Since there's no IPMI, support for peripherals that is based on an extensible plugin model, because of course there are always going to be more peripherals that we will have to support in one way or another. We won't be able to implement it ourselves. And finally, we decided that those devices had to leave the data center, right? So it's not going to be all owned by Chameleon, owned and operated by Chameleon. But our users who want to operate those devices, right, we're going to give them an SDK, connect that the devices to a virtual site, and provide restricted sharing. And I'll talk about restricted sharing a little bit more later. And we made this available, this implementation of the testbed, again, based on OpenStack or adaptation of OpenStack, made it available in June, and we're adding new features throughout June. And at the beginning of September, we had a workshop, and the remarkable thing was that in those 2 months that the testbed was available, there were 8 applications that were running on the testbed that then later presented on the workshop. And some of those applications we knew about because they were our users before, and in a sense, they are the ones that we built the testbed for. But some of them we did not know. We met them at the workshop, or we met them when they submitted a white paper for the workshop. So within 2 months, so that was a tremendous uptake of an edge testbed, and generated a lot of feedback that we're still churning on. Some surprising conclusions, some of which I will also share later. But restricted ownership or restricted sharing was actually one of them. And it's something that gives us food for thought and something to develop and improve on later. Okay, so what does an edge testbed look like? So other than those features that I enumerated, we're thinking about it as a horizontal platform that can be deployed on our devices, can be deployed on our user devices, but a horizontal platform with a very firm end, as non-prescriptive as possible, in order for our users to run a variety of experiments on top of that and come up with a variety of solutions, right? So in particular, we're not networking people. We don't solve those problems. We collaborate with networking projects that do, right? That's their horizontal solution. There are people who work on power managements or operating systems for the edge. We want to work with them. We want to enable their solutions to serve the community better, right? And if we come up with enough layers of such software stack, then we can possibly package them together and offer to application users something that might work and might be a new novel capability in their area. So this is just a few questions, a few nice pictures. We came from computers in the data center to a little edge configuration in the field, which originally was just wherever our developers happened to be. Okay, so to reiterate the capabilities now in the context of the same experimental workflow that I described before, we have very modest resource discovery capabilities right now, but the allocation capabilities for edge devices in Chameleon right now are pretty much exactly the same what they are for the devices data center. Reconfiguration is a little bit different, because instead of bare metal reconfiguration, we're deploying containers on those devices. But for those containers, we also provide a catalog of images. We also support snapshotting. And very importantly for our users, we support Jupyter integration. So you can have this modus operandi where you go from edge to cloud within one Jupyter notebook, right? And people do that for a variety of reasons. Sometimes they store data in the cloud, sometimes they train their models in the cloud, use them on edge devices, and sometimes they just have distributed experiments that span the edge and the cloud. A quick note about sharing devices and support for restricted leases. This is something that came with great force when we were working with our users. Many of them say, and I'll give some examples shortly, many of them say, we would like to add those devices to the testbed, but we don't want to share them with everybody. Why? Because those devices are connected to various IoT capabilities that are specific to a certain application, right? So they may be part of a self-driving car, for example. It doesn't make sense for somebody, very distributed, very remote, who's not part of a class that is learning about self-driving cars to get access to that. So this is very interesting, and essentially makes the testbed capability very project specific. This is a very different conception of the testbed than what we started out with, right? A pile of hardware in data centers. So as I promised, a few examples of what our users were doing. So one of them were self-driving cars with Keahey. So this is a project by Rick Anderson from Rutgers University. He teaches classes using self-driving cars, the cars that you see in the picture there. And those classes were very complicated for him to teach because you have to add those cars to the network. You have to figure out which car is which, somehow give student access. So there's a lot of churn, a lot of logistics that the instructor had to do. Now with Keahey, well, that car, each car is tied to a Raspberry Pi. Those Raspberry Pis are edge devices that we can allocate. So what he did is he took the SDK, the Keahey SDK, installed that on his cars, and now the students can make advanced reservations for specific cars, the cars that are tied to an edge device, and they can interface them via the Jupyter notebook. They can drive them. They drive the car around the track, and they check how their machine learning algorithm responds to change in the various different tracks, and so on and so forth. And they can collect the results, put them in the cloud. And most importantly, he can package and share the course modules that he developed, right? So he can share it with other instructors. He can share the general modus operandi for his class with others, and so forth, right? So it's an interesting educational applications. And now here's what those cars might look like when they grow up, right? They may become tractors in precision agriculture, or agricultural bots, right? So there's an agrobot in the bottom left picture, right? So it's equipped with multiple cameras and something that drives around the field, and it looks at plants and does phenotyping. So in other words, visually assesses those plants and reasons based on that observation, what's happening with those plants. If they need more watering, or if they need more fertilization, or things like that. So those precision agriculture projects are working with very recently funded new project called ARA. This is one of the power projects, a testbed for for wireless research, and it has a particularly challenging goal, which is to find a way to provide cheap wireless in rural areas. This is very, very hard, right? Because there are very few subscribers and very far in between in rural areas. So they've got a big challenge. They are installing infrastructure specifically to support that, and specifically ultimately to support those agricultural applications. And they're working with us. They decided to adopt Keahey and Qi, so Chameleon infrastructure in general. And they're also working with us on developing Keahey to provide spectrum reservations. But that's something that they want to provide as part of their projects. And they are configuring a separate from Chameleon Keahey site, a separate but federated. So again, you will be able to ultimately have experiments, again, from one Jupyter notebooks that span both testbeds. Another quick example, this is a group from Florida International University. Those are marine biologists who are interested in mapping existing fish populations. And they wanted to research various strategies for their edge installation. When they started talking to us, the idea was that they were going to have Raspberry Pis on the floats that you see in the picture there. And those Raspberry Pis are going to be sending data to the cloud that will be running YOLO for recognizing a machine learning module for recognizing various different fish populations. But then they started experimenting with various different edge devices that we gave them access to. And they said, oh no, we're not going to use Raspberry Pis, we're going to use NVIDIA Nano. And that covers us, that actually enough for us to do all the recognition that we want on the boat. We don't have to go to the cloud, much better for us. And then last project is a project with drones, the FlyNet project. It's one of the NSF CC Star projects. And the challenge there is, how do we integrate compute and networking infrastructure and in-network processing for applications that change dynamically, right? So drones are coming in and out of range of various different networks. And they're using Keahey for a variety of experiments. They actually were using the Keahey deployment in the data center. But very importantly, they hope to provide tools that allow researchers to include Keahey base in their workflows, right? So somebody like one of the marine biologists from the previous slide, Keahey is very low level for them, but packaged with some way of managing their applications on that deployment and managing networks, and packaged with all the tools they need in order to run their applications, that makes the difference from a very high entry barrier into a new area to something that is feasible and can be deployed and generate good scientific results, right? So this sharing aspect and providing to the community things that you have is very, very important to us. It's something that we want to support. And it goes back to, I said at the beginning, one way for a testbed to generate impact is leverage the fact that everybody comes to the testbed to do their research and facilitate sharing between different communities and different areas of expertise. Okay, and so a few words about testbeds as sharing platforms, right? So we sort of addressed this question, came to the question by asking, can experiments be as shareable as papers are today? So today, when I do research, when I embark on a new area of research, I go and I read papers and I see what others have done, what questions have been answered, what questions have not been answered, to what extent have they been answered, and so forth. But I don't rerun people's experiments, generally speaking, largely because the artifacts that are necessary to do so are not available, right? So, so I don't do that. It's hard to do. Even if they were available, it'll probably take a lot of effort to do that and might not work out in the end. It's just logistically complicated. But is it possible to do? And we were thinking, we have a testbed, so we have a platform on which people can allocate the exact same resource on which an experiment has been run, right? What can we do to facilitate that? So one thing we noticed is, just by having a testbed, a public resource that anybody can come to, and yes, allocate the same the same node solves part of the problem, right? Because it's no longer the case that I have a cluster of GPUs in the basement of my computer science department and you don't. And so you can't reproduce my experiment. So it solves that problem. Now everybody has access to a cluster of GPUs. The cloud paradigm by itself helps because the way clouds operate is you deploy a pre-configured environment on cloud resources. And this is not true when I'm doing something on my own laptop, right? It's going to be very hard for me to fully describe the configuration of my laptop. Even worse on a node in a lab or on some workstation in a lab. Somebody else may have configured it. I don't know what's there, right? But in the cloud, all that environment is very nicely packaged in an image. So just by using the clouds, we're going a long way towards making an experiment repeatable. So what is missing? What is missing is the actual experiment itself. Something that connects all those pieces, says this image was deployed on this hardware and then this experiment was run. And various bits and pieces making the whole thing easier and so forth. So to recap a little bit what we do in Chameleon by way of facilitating that. So first of all, hardware is versioned. Again, it's versioned. We've had over 100 versions over the first 5 years of Chameleon. Because our users, Chameleon is a cloud, right? So our users use images and then they use some form of orchestration, whether that's Jupyter or whether that's OpenStack Heat, right? So because they use the cloud, they generated hundreds of thousands of images that are available for repeating things and many thousands of orchestration templates, right? So that's already there, that's available, that just needs to be labeled for somebody to use it in repeating an experiment. And so then we packaged, integrated the testbed with Jupyter and developed ways to share those experiments that I'll explain now, right? So first of all, this idea of sharing ideas or bundling together some sort of explanation, the process and the result is called literate programming. It's something that Donald Knuth defined a very long time ago. And today's most popular implementation of that is Project Jupyter. And so that was fantastic. But from our perspective, Jupyter has one shortcoming, which is that when you run those code cells, when you run your program, it's executed in a Docker container. Now, our users, they don't want Docker containers by themselves. They want something like this, right? You've seen it on the previous slide. It has all those switches, networks, and nodes combined together. So we integrated Chameleon with Jupyter in such a way that you can create those complex environments from your Jupyter notebook. Right? There's a little program that shows the story of the experiment. And then also we developed methods to provide sharing for that. And again, we've got a little paper that explains more about this. So there's also a logistical barrier to sharing experiments. We have the Jupyter notebook, but let's say I see a really exciting experiment in a paper somewhere and I don't have access to Chameleon, and it's jumping through various hoops in order to get it. So in order to lower that intro barrier, we implemented something called Chameleon Day Pass, right? So let's say you have a paper here. There's a fake paper that we wrote that has a power management experiment on it. In the figure caption, it says, click here if you want to repeat it. It goes to our experiment storage called Trovi, which is like Google Drive for experiments. And in there, you can request Chameleon access for repeatability, right? That request is going to go to Project PI. Project PI is going to give you access for a short amount of time. That is enough to reproduce the experiment. And then you're going to get an email that says, when you click here, clock starts ticking on your access and you can experiment with that particular Jupyter notebook. So then you can reproduce them because you can package them and you get access via Chameleon Day Pass. What's next, right? So next, we would like to publish those experiments So you can reference them from your paper, or others can reference them from their papers. And that requires us to think about the publishing ecosystem a little bit differently, right? So we started out with writing papers, they were put in proceedings were put in libraries, and then they were indexed in some way. Now, we're looking at something slightly different, because a paper, when I read a paper, I can read it by myself unaided, right? An experiment has a digital form. It's zeros and ones. And so we need a little bit of help to interpret those zeros and ones in some way. And for that, we're going to need something like a testbed, like Chameleon, for example. It's not that different to our existing ecosystem, right? Because if you were to check out not a paper, but let's say a microfilm from a library, right? The library would probably provide a microfilm reader for you, right? So all we're saying is we've got various digital representations of experiments, and we also provide a public resource, a publicly available resource on which you can reproduce those experiments. And we integrated with Zenodo, which provides the digital object identifiers for digital artifacts, and allows you to publish those experiments, right? So you can share them via Trovi. Later on, you can publish them via Zenodo and cite them. Okay, and last slide here. So a few parting thoughts that I'd like to leave you with. So one is that science is constantly in motion, which means that scientific instruments constantly have to develop, right? Constantly have to reach out to new frontiers. It was a very interesting thing that we noticed when we went from cloud to edge, right? So before, when we think about testbed, we think about it as a pile of hardware, usually very expensive hardware. So the nodes that we're putting into Chameleon now can be can go as high as $40,000, $50,000 per node, right? Those are nodes that have multiple GPUs on them, that have Optane memory on them, very expensive. And it makes sense to put resources like this in a testbed, because the use by a community that is 6,000 strong amortizes that cost, right? And also democratizes access to resources. That means that you don't have to work in a supercomputing center in order to get access to resources like that, right? So hardware was the main draw for a testbed. Now our users are telling us, we don't want hardware. We have hardware. We have hardware, we have a lot of it because it's quite expensive. The edge devices are inexpensive. What we want from you is a good way of providing sharing of those devices and connecting them to something like a cloud, to something like a wireless testbed, to something like core reconfigurable networking testbed, right? So it's a different way of thinking about a testbed. It's no longer hardware. It's more how do we share things? And in this new environment, sharing your research is more important than ever. One, the benefit is biggest because we're talking about an emergent area, IoT and edge computing. But also what we noticed is that the community is much more incentivized to share, right? In the more traditional areas, very often authors package their experiments and the interest in reproducing them is relatively low. What we noticed after the workshop is that there were many follow-ups that were saying, oh, can so-and-so make their self-driving car teaching modules available? And so did a great study of transfer to edge devices. Could they make that experiment available as a Jupyter notebook? I would like to run it on my edge device. So there's a lot more incentive coming from the community wanting to beg, borrow, or steal the work that others have done and jumpstart their own research based on what they're seeing. And so really it takes a village now to conquer this new frontier. And so last thought is think big. We're going to be there right there with you. And that's all I have for today.
Thank you so much. That was an excellent talk. Really amazing stuff you're doing there. So I would be happy to take questions from the audience next. You can either put them in chat or you can just unmute yourself. I'm going to stop the recording here.